Okay, so the type of trees that we use, generally speaking, in computer science are binary search trees. You can use trees to represent other things, such as like family trees, where you're showing the hierarchy, where you have a parent and then the child. So you may be already familiar with that, and you are allowed to interchange the terminology here. You can either refer to them as branches and then leaves of the branch, and then you could also refer to it as like a parent and child relationship as well. What we do always refer to though is the top one as the root node, hence that sort of tree terminology. But if you were to sort of refer to it as a parent child, you wouldn't lose marks. That is acceptable. Again, if we have an empty node, we refer to that as null or -1. So when we're adding to this, it's special because we're using binary logic. We therefore take the root node and we make a comparison. Is the data we're adding less than or greater than that particular piece of data? So if we look at this from a numbers point of view, it's more obvious what's going on. So we've got 30. We then want to add 15. 15 is less than 30, and therefore we add it to the tree. 45 is greater than 30, and therefore that gets added to the tree. If we wanted to then say add in 20, 20 is less than 30, so it goes to the left-hand side, but it's greater than 15, and therefore goes to the right-hand side of 15. You can see that we've got two empty spaces on either side, so there's no current data less than 15 and no current data greater than 45. In other words, what we're doing is whenever we are adding to a tree, we keep repeating this process. We're checking whatever current node we're on, and therefore we then, is it greater or less than? And if there's a null place, we can put it into the null place. So just to demonstrate that, I'm going to add a number here. So we're going to add 10. So 10 is compared with 30, less than, so therefore goes to the left-hand side. Is compared with 15, is less than, and therefore goes to the left-hand side. And then is then added to that null place. You can see here. And then technically there are two null spaces come off. There is, to be truth, a null space coming off the 20 and the 40 as well. But they don't tend to get drawn because it'd be a bit of a pain, wouldn't it, to have to actually draw them all out. But it's worth remembering there is now two empty nodes available for us to put in another number. If we can also do this with letters as well. So we treat alphabetical order. So in other words, earlier in the alphabet would be less than, later in the alphabet would be greater than. So therefore, Violet is after Rick in the alphabet and therefore would go to the right-hand side, whereas John is sooner than Rick in the alphabet and therefore would go to the left-hand side, and so on and so forth. If we're going to delete, this is more special because we need to be considerate of what's going on in the graph. What we must always do is preserve the order. When there's no branches coming off, it's actually incredibly easy because by removing 40 doesn't impact on any of the data, we just remove it. That position has just become null. However, if there are branches, we then have a bit of a problem. Often in binary search trees, the left-hand side is given priority, and therefore I would advise that you always try and give the left node priority. Just as a habit, what you don't want to do is start swapping backwards and forwards in the middle of an exam and then confuse yourself. So if you always just practice it from the left, it kind of feels more kind of usual method of doing it. But what we need to always do is make sure that we preserve the integrity of the tree. So in other words, what we mean by this is if we remove 15, if we were to move 20 up to that position, it would actually still preserve the integrity of the tree. But if we also move 10 up, as I've done in the example, again, it preserves the integrity, so it's okay. What we want to do really is just think about it from a practical point of view. So if, for example, 20 had more data coming off it, it's much easier to move the 10 element than it would be to move the 20. So again, we might want to vary whether we do the left or right side depending on the particular graph we're drawing, so the tree we're drawing in, and whether that's appropriate. Just on that, a tree is just a form of graph. Okay, it's just the layout of it just has this hierarchy layered element to it. With a tree, we want to be able to traverse it, so we have 4 different methods here. The key to remembering these is in the name. So in other words, the pre-order is based on when the tree happened in the order that you carry out the action, whereas the post-order is at the end, and pre being before, post being the end is just an easier way to remember them. So let's look at it first, what I mean. So our parent being the root node, we always deal with the parent first with a pre-order. So in other words, we would read through this. We'd look at the parent first, Rick. We prioritise the left-hand side, so then left will be John. We then go down again, looking for our next parent will be Adam. There's nothing else there, so we go to the left-hand side. There's nothing from Adam to the left-hand side still, so then we now go to the right, and then we get Ken. We've done all of the left-hand side, so now we go to the right-hand side. We therefore will go to Violet. We look to the left-hand side of Violet and find Tom. There's nothing to the right-hand side. We're done. Okay, our next one of these is in-order traversal. An in-order traversal is really good if you want to look at a tree and check have you added the data correctly. In other words, as you move from left to right, if you sort of move your finger across, if you like, the screen, you'll see that your finger will go over Adam first, then it will go over John, then over Ken, then over Rick, then over Tom, and then over Violet. In other words, it's going to read it in alphabetical order. So a very good, quick way of just checking have you done it correctly. What's actually happening from the computer's point of view, though, is it's going left, parent, right, left, parent, right as a pattern. In other words, we go down the left-hand side until we can't get any further. We get to Adam. We then go to the parent of Adam, John, and then we go to the right-hand side and see if there's anything there. There is, so it's Ken, and therefore we do Ken next. We then go up, there's nothing else there, so we go now up to the parent, which is Rick, and then we look to the right-hand side. However, before we interact with Violet, we check, is there something to the left of it? And there is. So therefore we go to Tom first, and then back to the parent of Violet, and then if there was anything right hand side, excuse me, there isn't, and therefore we've completed it. Our next one is post-order traversal, and like I said, the key to remembering this now is that the parent is dealt with last. Okay, so therefore we're going to go Adam, Ken, John, because Adam and Ken are the left and right, and John is their parent. So Adam, Ken, John. We then go John. We're looking across at Violet, but because there is something to the left of Violet, we prioritise that first. So in other words, we go John, Tom, Violet. There's nothing to the right-hand side, and therefore we go to the parent of Violet, which is Rick. We also have level order, and with this one, all we're doing, this is probably the easiest way to read. We're literally going to start at the top, so Rick, then we're going to do John and Violet, and then Adam, Ken, Tom. Really quick, nice and easy to do. Okay, so when we're storing the data for a binary tree in memory, we have a couple of ways we can do this. Our first method will be to use an array, just like we've got here. You can see with this that the data is being stored in each index, and in other words, the first piece of data is our root node there. What the advantage of this is that it's very low memory usage, because for each piece of data we just taking up that one sort of index within the array. However, to actually create the tree is more processor intensive, because we now need to then compare each data with the previous sort of elements of the tree. And obviously that could take a long time if it's a large data set. So in other words, what I mean is that we've got 17 already as our root node. Our next one then is 8. 8 is less than 17 and is therefore added to the tree. 4 is then added, so is less than 17, less than 8, and then is added to the tree. 14 is then added, it's less than 17, but it's greater than 8, and therefore is added to the tree. And then I'll stop at 22, but 22 is greater than 17, and therefore is added to the tree. Our second way of storing memory and data is to use the table on the right hand side here. This is actually a linked list, or it's very, very similar to a linked list. So what's actually happening here is that you can see that on line 0 within our list, we have the data of 17. That data is the root node because it's on line 0. So we then have a left pointer just there, oops, for some reason, and then a right pointer there. If we look at the left pointer points to 1. That isn't data, instead it's actually row 1 in the list. on row 1, the data is 8, which therefore links to that piece of data there. If I just go back to 0, so I've written all over this now, so it's harder to see, but the 4 here is to the right side of the data, and therefore, again, that 4 is referring to the line here in the table, and to the right-hand side of 17 is 22, which when you look, it is. Okay, but I just wanted to point out again that when we talked about the array, we said that was low memory usage but high processor usage. With the table, we've got kind of the opposite. So we've got high memory usage because we need to store all of these different elements, so the left pointer, the data, and the right pointer. But there's no comparison now needs doing. We just literally read from the list, and therefore we can easily create the tree. So again, we've got an efficiency element to this as well, which is worth considering in the way that we choose our data structure of what's appropriate each time. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.